In this video, we're going to look at an example which is going to allow us to recap some of the concepts that we introduced last time, where we were trying to understand how to quantify how fast a reaction happens. So in this example, what we're asked to do is determine the rate law for the reaction between nitrogen and oxygen using the data that was shown in the table below. We're asked to find the overall reaction order and determine the value of our rate constant. The information that we're given in the table describes 3 different experiments where this reaction was performed and the initial reaction rate was measured. In each of these experiments, the initial concentration of the reactants was varied and the initial reaction rate was measured. It's very important that we actually specify the initial reaction rate here, because as this reaction occurs and the concentrations of the reactants decreases, we'll actually see a decrease in the reaction rate. This really motivates why we're interested in determining rate laws, and it's because the rate law allows us to determine the rate of reaction at any concentration. And we can do this if we know the reaction order, which tells us how the rate will vary as we vary the amount of our reactants. And we need to know the rate constant, which is this proportionality constant between this factor of the product, this factor of the concentrations and the reaction rate itself. Importantly, our rate constant is independent of concentration, and so the same rate constant and indeed the same reaction order will apply for the conditions in all 3 of these experiments. So let's start by writing down a generic rate law for this reaction. So our rate law starts off with our rate constant K. Our first reactant is nitrogen. And so we have the concentration of nitrogen here, and we have to raise that to the reaction order with respect to nitrogen. So we'll call that M. And our other reactant is oxygen, so we also have to multiply by the concentration of oxygen. And again, we have to raise this to the power of its reaction order, which will give the symbol N. So we have several components that actually go into this rate law. So let's take a slightly closer look at each of these components to make sure we know exactly what they mean. The first component K, this is our rate constant. And the rate constant is concentration independent. The rate constant itself can have units which span a very broad range of a combination of concentration and time, but in every rate law, the rate constant will have units which allow the actual rate and the product of these concentrations to give rise to unit consistency. So we have to know what the reaction order is in order to determine what the units of our rate constant are. So we'll look at the end of this example what the units of the rate constant for this particular reaction must be. The next components of our rate law are the concentrations of the reactants. So we have the concentration of N2 and the concentration of O2. These can be reported in any of the key units of concentrations. Typically they're reported in molarity, especially for things that are occurring in a solution. In this case, these are actually gas phase concentrations, but we're still told here the concentrations in molarity units. Finally, we have M and N, which are the reaction orders. We have an order with respect to every reactant, and the reaction order, the overall reaction order, is actually equal to the sum of the orders with respect to each individual reactant. So in this case, we have 2 reactants. The overall reaction order is going to be the sum of the orders of each individual component. So having now established the rate law for this reaction, we're in a position to start using some of the experimental data that we're given to actually determine the values of K, M, and N. The procedure that we have to adopt to do this is to look at the different experiments that are occurring and identify pairs of experiments that allow us to simplify the rate law down and actually calculate some numerical values for the different components. What you'll notice by looking at the concentrations here is that between different pairs of experiments, we're only actually changing the concentration of one component at a time. If we compare the reaction in experiment 2 and 3, for example, we're changing the concentration of N2. Between experiments 1 and 2, we're changing the concentration of O2. So this kind of sequential experimentation, where we're changing the concentration of only one reactant at a time, this is what actually allows us to determine the value for the different components of our rate law. And the way that we do that is by taking ratios of the different experiments. So we're going to start by looking at the ratio between experiment 2 and 3. And what this is going to allow us to do is determine the reaction order M, which is the reaction order with respect to nitrogen. So let's start by writing down what the rate law ratio of these two experiments is going to look like. What we mean by the rate law ratio is essentially the rate of experiment 2 divided by the rate of experiment 3. So let's take a look at what those look like. We're going to be using our generic rate law that we've written down here. And so for experiment number 2, we have K. Now remember, K is independent of concentration, so for all of these experiments, K is going to be the same. Then we have the concentration of N2 in experiment number 2 raised to the power of M multiplied by the concentration of O2 in experiment 2 raised to the power of N. On our denominator, we have the rate law for experiment 3. So we have K. This is the exact same K as in our numerator. We have the concentration of N2 from experiment 3 raised to the power of M. And the reaction orders are also going to be the same between each of these experiments. So we have to just write down M. We don't need to signify which experiment it actually comes from. And the final term is the concentration of oxygen in experiment 3 raised to the power of N. Now, because we've chosen our experiments such that the concentration of one of the reactants doesn't change, what it means is that we can actually cancel out a lot of the terms in this expression. We've already said that the reaction rate constant K is the same for each one, so we can cancel K immediately. And we've also chosen our experiment such that the concentration of oxygen is the same. So we can also cancel out these terms relating to the oxygen. So now we have an expression where we're taking the ratio of two rates, both of which we have the numerical values for, and we're taking the ratio of two concentrations. Again, we have the values of those concentrations. So the only unknown is this M, which our concentrations are raised to the power to. In order to rearrange this expression and actually solve it, we have to use logarithms. So we're going to take the natural logarithm of both sides of our expression here. So we're going to take the log of rate number 2 divided by rate number 3, and that's going to be equal to the log of the concentration of N2 in experiment 2 raised to the power of M divided by concentration of N2 in experiment 3 raised to the power of M. Now, because each of these terms are raised to the power N, what we can actually do, instead of writing each term raised to the power of n, we can actually combine them together and say that this is the same as this entire ratio being raised to the power of m. This means exactly the same thing. We can also now apply some of the rules of logarithms, which tells us that if we're taking the log of something and that something is raised to the power of another thing, then this is actually equivalent to that other thing, in this case m, multiplied by the log of that subject. So by using the laws of logarithms, we can rearrange this expression to be equal to m multiplied by the log of n2 in experiment 2 divided by n2 in experiment 3. And this is still equal to the log of rate 2 divided by rate 3. So we're now at a position where we can simply rearrange this expression and solve for this term m. So let's just do that over here. We have now m is equal to the log of rate 2 divided by rate 3, all divided by the log of n2 in experiment 2 divided by n2 in experiment 3. So let's put some numbers in here. We're taking the log of 500 divided by the log of 125, and these have units of molar per second, and we're dividing by the log of the concentration of N2 in experiment 2, so 0.04, divided by 0.01, the concentration of N2 in experiment 3. Now you should see now that the ratio of our numerator and our denominator here actually are the same in both cases. Both of these are the logarithm of 4, and so this actually cancels down to be equal to just 1. So this whole process has told us that the reaction order with respect to nitrogen is equal to 1. So this is our reaction order with respect to N2. We can repeat this procedure to determine the reaction order with respect to oxygen. And to do that, we have to choose our pair of experiments accordingly. So we'll choose the pair of experiments where we can repeat this same cancelling procedure, but for N2 rather than O2. So the pair of experiments that we'll be cancelling are the experiments 1 and 2. So we can again write this expression out where we're taking the ratio of the rate of experiment 1 and the rate of experiment 2. We can cancel out k's, and we can cancel out, in this new case, the N2's, and we'll get an expression for n which we can rearrange into a form that looks very much like this. So when we actually do that, what we have will be n is equal to the ratio, or the log of the ratio of rate 1 divided by rate 2 divided by the log of the concentration of oxygen in experiment 1 divided by the concentration of oxygen in experiment 2. Now let's plug some numbers in again here. In experiment 1 we have the rate 707 divided by the rate in experiment 2, which is 500, and we're dividing by the log of the ratio of oxygen concentrations, which is 0.02 divided by 0.01. Now we don't have quite as simple a fraction here as we did for our m value. When we actually determine the value of this ratio, what we find is that we actually get a number which is 0.5. That's fine, reaction orders don't need to be integer values. What this now tells us is that our overall reaction order, is equal to the sum of these, 1 plus 0.5, which is equal to 1.5. And we can write our rate equation as k lots of n2 to the power of 1 multiplied by O2 to the power of 1/2, or 0.5. Now this rate law looks a little bit different than what we may have seen before, but just because we have this fraction in our order here doesn't change anything. We still deal with it in exactly the same way. So the last thing that we have to do now is actually determine what the value of our rate constant is. And we can use any one of the experiments from our table in order to determine our rate constant. All we need to do is plug the numbers into our rate law here and solve for k. So let's choose experiment 1 and we'll plug the numbers into this expression. So our rate in experiment 1 is 707 molar per second. That's equal to k multiplied by the concentration of N2, which is 0.4 molar, multiplied by the concentration of oxygen, 0.2 molar, raised to the power of 1/2. So now we can just rearrange our expression to get k is equal to 707 molar per second divided by 0.04 molar multiplied by 0.02 molar, all raised to the power of 1/2. So we have units here which are going to look a little bit non-standard compared to what we've encountered before. We can numerically calculate that our rate constant is 1.2 times 10 to the 5. And when we cancel out our units, we can cancel our molar units from top and bottom. We have our seconds to the -1, and we also have this molar raised to the power of 1/2 on the denominator. So our units are actually going to be molar to the -1/2, seconds to the -1. And this is the rate constant that describes this reaction. So just because it has slightly non-standard units, it's still a rate constant, and those units are simply there in order to make sure that the overall unit analysis works out consistently. So we've now identified all three factors that go into our rate equation. We know K, we know the reaction orders with respect to each reactant, and so we can use this rate law to determine the rate of this reaction at any concentration of reactants N2 and O2.